In this problem, we have a couple of charged particles, one here and one here, that are 20 centimeters apart. And we're asked to figure out what the electric field generated from these two charged particles is at two different points here, A and here, B. A is directly in between the two particles. That makes it a little easier because of symmetry. We know that because they have the same charge, we know that these two vectors, the horizontal component here will cancel out, and we'll just have a net result vector in the vertical direction. So the charge is 4.7 microcoulomb each here and here. And basically, this problem comes into just a bunch of vector algebra, some vector addition, and then getting the magnitudes and directions. So for point A, we can write down the electric field vector generated by this particle, and then also the one generated by this particle. The angle here is theta, and also here is theta. So we can see that they have the same magnitudes, and their directions they have opposite direction in the x direction, but in the y direction, they are they have the same sign. So when we add these two vectors up, the x component drops out, and we get 2 times the y component. So we get a vector in the vertical direction. Now we can use, instead of actually calculating sine of theta, we can just use some trig identities to figure out that the sine of theta is let's see here, is this distance here divided by this distance here. So this distance here was 5 centimeters, and this distance here is whatever the distance from the particle, from the charge to the point is. And that distance also shows up here, obviously, in the magnitude. Let's see here. If we plug that into here, we just get, we wind up with 10 times k times q divided by d cubed in the j direction. And so j is a unit vector, so that the coefficient out front of it is just the magnitude. So the magnitude is 10kq over d cubed. And if we plug in numbers, we get 3 times 10 to the 6 Newton per Coulomb. And again, if we're measuring from this x-axis here, then the angle here is going to be 90 degrees because it is vertical. Now, for the second point, B is a little more difficult because obviously we don't have symmetry here that allows things to cancel out, but it's still just vector addition. So the vector field generated by this charge is given by this, where now this angle here is theta 1. And then the vector field here is generated from this particle is this, and here is the angle theta 2. So these are the two vectors, and we just need to add them up. We can also use some trig identities just to get sines and cosines in terms of our dimensions here. So this one is 45 degrees, so we have cosine of theta 1 and sine equals sine of theta 1, and those are both 5 over the distance from this particle to the point here. Cosine of theta 2 is this distance here, which is 15 centimeters, divided by the distance between the particle and the point. And sine of theta 2 is this distance here, divided by that distance. So we can plug all this stuff in to here, and then add these up, and this is what we get as the resultant vector. And we can see we have kq in every term. We could factor that out, and in fact, we have numbers for all of these things, so we can figure out the magnitudes then. So in the x direction, we have 4.38 times 10 to the 6 newtons per coulomb. So actually, we have our net resultant vector actually has an x component, a positive x component. So we're going to be this way. I didn't draw this particularly well because this should be more 45-degree angle here. So this vector should be more like this. again, the scales aren't quite right. And then in the x direction, or in the y direction, we can see that, well, in the x direction, we can see that we get a subtraction here because the x component of this one is in the negative x direction. The y components are in positive direction in both cases, so we get this term here. And so then we calculate, plug in all the numbers there, and we get 6.51 times 10 to the 6 newtons per coulomb, and that's the J component. Now, to get the magnitude, we just take the, the square root of the sum of the squares of the components, and that winds up being 7.85 times 10 to the 6 newtons per coulomb. And to get the angle, we just, use the arctangent, and we figure out that angle between this axis here and the resultant vector is 56 degrees, and that makes sense because we expect it to be at least 45 degrees, because we expect that vector, the resultant vector, to be between these two. So we know that it should be at least 45 degrees, and we get that it is indeed 56 degrees.